In this chapter, we're going to learn about identification numbers, which are numbers that encode information. Some examples of places where you'll see identification numbers is on money orders, on airline tickets, credit cards, and your social security number. For WCU, your identification number is your 92 number. In this section, we're going to look at ways of assigning identification numbers, which are called coding schemes. This is kind of a long section, so I'm going to break the lecture video up into two parts. The last digit of an identification number is often what's called a check digit, and it has to follow a certain rule to make it easy to detect errors in reading identification numbers. So the first coding scheme we're going to look at is called the division by 9 scheme. The U.S. Postal Service uses this scheme for identification numbers for money orders. Each money order has an 11-digit number. The first 10 digits are random, and the last digit is a check digit. So the last digit has to follow a certain rule. And in this case, the rule is that the last digit is equal to the remainder of the sum of the first 10 digits divided by 9. So let's do a little review of remainders. How do we find a remainder? Well, the remainder is the amount that is left over when we divide one number by another. So probably the first way you learn to find remainders is using long division. So here I'm finding the remainder of 103 divided by 9 by using long division. And I find that 9 goes into 103 11 times, and I've got 4 left over, so 4 is going to be the remainder. You can also use your calculator to find the remainder. It's a two-step process, so if you want to find the remainder of a divided by b, first you're going to enter a divided by b into your calculator. Then you're going to enter a minus the whole number part of the number you found in step 1, so leaving off any decimal part of the number, times b. And if you enter that into your calculator, that's going to give you the remainder of a divided by b. So let's look at an example of that. So if I want to find the remainder of 103 divided by 9, first I'm going to enter 103 divided by 9 in my calculator. And that's going to give me 11.44444. So for step 2, I'm going to take 103 and subtract the whole part from step A, so 11 times 9, and that's going to give me 4. So the remainder of 103 divided by 9 is 4. You can also use Google. This is an easy way to find remainders. So if I want to find the remainder of A divided by B, I'm going to enter A mod B into Google. So in this case, if I enter 103 mod 9 into Google, that's going to tell me that that's equal to 4. And we'll come back to this mod in next week. So let's look at an example of a money order. So this is a Postal Service money order, and I've got my rule up here. The last digit is equal to the remainder of the sum of the first 10 digits divided by 9. So here is my identification number. It's copied down from the money order here. So let's check the rule. First, I want to find the sum of the first 10 digits. So I'm looking at the sum of all of the digits except for the 6 here. And if I do that, I'm going to get 42. And then the rule tells me that the check digit should be the remainder of 42 divided by 9. And that's going to be 6. So my check digit should be 6, which it is. So that's a valid identification number for a money order. Now let's look at an example of detecting an error using a coding scheme. So suppose we have a money order with identification number 74389235125. I want to use the rule for division by 9 schemes to see if this is a valid money order number. So here's my rule as a reminder. The last digit is equal to the remainder of the sum of the first 10 digits divided by 9. So first I'm going to add up my first 10 digits. So that's going to be 7 plus 4 plus 3 plus 8 plus 9 plus 2 plus 3 plus 5 plus 1 plus 2, and I'm leaving off my last digit 5. If I add all of those up, that's going to give me 44. So now I want to find the remainder of 44 divided by 9. So I'm going to go the easy route, and I'm going to use Google. And it's going to tell me that 44 mod 9, so the remainder of 44 divided by 9, is going to be equal to 8. So if this is a valid money order number, then my check digit should be 8, but it's not. The check digit here is 5, so this is not a valid money order number. So we found an error in this case. How good is this scheme at actually detecting errors? That's an important question to ask. Well, we're always going to find single digit errors, and that's an error where just a single digit of the identification number is typed in incorrectly. What we're not going to find is any error where two digits are switched. Those will always be missed. So in this case, I've got my identification number here, and I've switched the places of 6 and 7 in these two numbers. So if I made a typing mistake and typed in 167 instead of 176, these both follow the rule for the check digit, even though the 6 and 7 have switched places. But if a computer is using the rule to check these numbers, then they're both going to come up as okay, so it's not going to catch that type of error. And this type of error is called a transposition error when two digits are switched. A similar type of scheme is the division by 7 scheme, and you'll see this in airline tickets and some rental car reservations. In this case, the rule is that the last digit is the remainder of the rest of the digits taken together divided by 7. So the identification number can be any number of digits, but we're just going to take all but the last digit and divide by 7, then the remainder should be the check digit. So if we have a car rental reservation number, which is 639811, first we would look at all but the last digit, so that's just 63981, and if we divide that by 7, the remainder is going to be 1, so that means the last digit or the check digit should be 1, which it is, so this is a valid reservation number. So let's look at an example of finding a check digit. So an airline makes a ticket number by randomly generating the first 11 digits and then using the division by 7 scheme to determine the 12th digit. So if I've got my first 11 digits of a airline ticket number here, I want to figure out what should the check digit be. So this is what an airline would do when they're coming up with your ticket number. They randomly pick the first 11 digits and then they use a computer to tell them what number would follow the rule to give them the check digit. So here's a reminder of my rule. The last digit, or the check digit, should be the remainder of the rest of the digits taken together divided by 7. So all I've got here is my first 11 digits. I don't have the check digit added on yet, so I'm just going to look at that. So I want to find the remainder of that divided by 7. So if I go to Google, I'm going to go 5109200386, and I want to find the remainder divided by 7. So mod 7, and Google is going to tell me that that remainder is going to be 4. So that means the check digit should be 4 for this airline ticket number. So the ticket number is going to be 510920033864. So that's going to give me my whole 12-digit airline ticket number. So how good is this method at detecting errors? Well, unlike the division by 9 scheme, this division by 7 scheme is not going to detect all the single digit errors where just one digit is typed in wrong. If you type in a 0 instead of a 7, or a 1 instead of an 8, or a 2 instead of a 9, or the opposite way around, then you're going to get the same check digit. So it's not going to detect that error. It does, however, detect most transposition errors where two numbers are swapped, except if you switch a 0 and a 7, a 1 and an 8, or a 2 and a 9. Those won't be detected. But it does catch most of those, so that's a little bit of an improvement. This is a coding scheme that you should all be pretty familiar with, the Universal Product Code, or the UPC. Almost every product that you buy is going to have a UPC code, which is a 12-digit number like this one here. And it's broken up, so you've got one digit, then a group of 5 digits, another group of 5 digits, and then the last digit, which is a check digit. So the first digit is going to identify the category of goods that the product is in. The next 5 digits identify the manufacturer, and the next 5 digits identify the product, while the last digit is a check digit. So this has a slightly more complicated rule. So before we get to the rule, we're going to label the digits of the UPC number as A1 through A12. So for this number here, I would have A1 is equal to 0, A2 is equal to 3, A3 is equal to 8, A4 is going to be equal to 0, and so on. So I'd label all of these numbers A1 through A12. So now I can state what the rule is. So for this, we're going to use what's called a weighted sum. So I'm adding up all of the digits of the UPC number, but I'm multiplying every other one by 3. And once I do that, that should be evenly divisible by 10, or in other words, that sum should add up to a number that ends with a 0. So this UPC number that we saw before, 0380000001277, is in fact the UPC number for a box of Kellogg's Corn Flakes. So we can see that if I take this weighted sum where I'm multiplying every other digit by 3 and add those all up, that's going to equal 60, which is evenly divisible by 10, so that follows the rule for the UPC code. Let's look at an example of a missing digit. So suppose one digit of a UPC number is scratched off of a package. You can read the number as 63492X136288, where the X is the scratched off digit. And we want to use the rule for UPC numbers to find the missing digit. So this is just a reminder of my rule. I'm taking this weighted sum, and it should be evenly divisible by 10 or end with a 0. So first I'm going to label all of the digits of my UPC code. And I've done that here, so I've just rewritten the code so that I can clearly see what each number is. And I noticed that my scratched off number is A6, so I've got an X there. So then I'm going to plug all of those numbers into my rule and get this sum. 3 times 6 plus 3 plus 3 times 4 plus 9 plus 3 times 2 plus X, whatever my mystery digit is, plus 3 times 1 plus 3 plus 3 times 6 plus 2 plus 3 times 8 plus 8. So if I add all that up, if I add all of the numbers except for X, I'm going to get 106, and then I've also got my scratched off digit X that I need to add in there. Alright, so to follow the rule, I need to find a number X that's going to make this end in 0. So the next number that ends in 0 is 110. So if I want 110 to be equal to 106 plus X, then if I subtract 106 from each side, that's going to tell me that 4 is my scratched off digit. So the digits that's missing should be a 4. So let's talk about error detection for UPC codes. UPC codes can detect all single digit errors where just one digit is typed in wrong. And it can detect 89% of all other types of errors. So including most transposition errors where 2 digits are switched, but not all transposition errors. So if we have an error of this type, where I've got 3 digits ABC and I switch the first and the third digit, then that error is not going to be caught. So if I have a correct UPC number like this one, and I accidentally type it in wrong, so I switch the 3 and the 5, this is also a valid number. It's going to follow the same rule even though those 2 digits have been switched. They use a similar coding scheme in Europe called the European article number. And this is a 13-digit number, so we can label the numbers of the EAN code as A1 through A13. And it follows a very similar rule. So again, we've got a weighted sum where I'm multiplying every other digit by 3 and then adding them all up. But here I've got 13 digits, so I've actually added an extra digit on to the front here. And this should also be evenly divisible by 10 or end with a 0. So you can actually make a UPC code into a EAN code by just adding a 0 on the front. And starting in January 2005, US retailers were required to have software that could read both the UPC and the EAN codes. So this will finish up part 1, and we'll look at the rest of this section in the video for part 2.